CLion, a cross-platform IDE for C and C++. Download now.
Okay, I have a lot of slides and I have a lot of information to dump on you. And my talk is about integer log base 2, the Bruijn sequences, and some x86 instructions. So what is the Bruijn sequence? Here is the Bruijn sequence for alphabet 0 or 1, or otherwise binary, and order 4. What does it mean? It means that we have a sequence of digits, and if we go 4 digits at a time, one subsequence after another, we get all the combinations of bits in our 4 bit chunks that can be represented in 4 digits. And the sequence is cyclic. So after we go to the end, we add the same sequence right to the right of our primary sequence, and we basically get the digits from the beginning of the sequence. What can we do with that? We can hash powers of 2. For example, if we multiply our sequence with the power of 2, this is basically the same as shifting our sequence left. And here we multiply modular size of the our number. Basically, we shift left. Then we can get 4 leftmost most significant bits, and here that way we get a hash value that with help of which we can hash our powers of 2. We get unique hash values for every unique power of 2. So this practically is a perfect hash. So now we can use it to implement logarithm. We could, before applying this trick to round our arbitrary number to the highest to the next highest power of 2. This is the algorithm that I got from twiddling hacks. Great site. I recommend it to you. So here is the actual algorithm or procedure from that site, which doesn't use rounding to the next power of 2. Rather, it uses rounding to 1 less than a power of 2. And we don't need these 2 unnecessary instructions because we don't need to actually round to the next power of 2. We can just fill all the ones after the most significant one, basically rounding to 1 less than a power of 2. We save on instructions, and we can use this to use the De Bruijn sequence to multiply with it and to shift to get 5 most significant bits, and to use that result to look up in that table for actual results of logarithm. So yeah, here's code zoomed in. The De Bruijn sequence is that number that we multiply with. Then we convert that result to uint32, then shift, then with the result of that we look up in the pre-computed table of logarithms. Basically, here's how it looks in this example. We have our arbitrary number rounded to 1 less than the power of 2. We multiply with our De Bruijn sequence. We got the result. We get the 5 more significant bits, and we use that result to look up the logarithm. bit twiddling hex site does not suggest or does not provide a solution for 64 bits, only for 32-bit integers. But internet wouldn't be internet if someone found. Oh yes, I had to say that we can't use any De Bruijn sequence for this task because we multiply not only by a number containing 1 bit, but a number containing all the lower least significant bit set. So we have to make sure that the result of the multiplication is unique for all the numbers that are one less than a power of 2. So you can easily, by brute force, for example, find all the 2-bit constants for that, but it is not non-trivial, and I don't know about a general algorithm that can allow to find constants or De Bruijn sequences for 64 bits. But someone named friend G found one constant for 64 bits. Yay, yay the internet, and we can use it. So here is our code. We have a constant that I named friend G. We can have initialization of our table with which precomputes all the necessary lookup values. We here we have our logarithm algorithm procedure. Basically, it uses only multiplication and shift and lookup, but also uses 6 shift and ORs, logical operation, bitwise and logical operations. And this way we can calculate logarithm base 2 of 64-bit integers. You can ask, why do we do all of this if we have count leading zeros? And indeed, we can use count leading zeros to implement the same logic. Here, I add the logic to accommodate to get the same result for 0 input, for 0 value. And we can use XOR, exclusive OR, instead of subtraction here to save on a couple of 186 instruction. And let's benchmark it. Let's have a dummy function that basically does nothing except converting into 64 to int 32. We have our random device with which we generate random numbers. We have benchmark for our dummy procedure that does nothing. We have our benchmark for our log2 that uses De Bruijn sequences. We have benchmark for log2 using count leading zeros. And here is the result. This is for MSVC, and this is for Clang. Clang optimizes everything away, so we can't really measure what's going on, so we have to do something about it. Let's, instead of calculating one value, calculate in sequence, for example, for 1,000 values, 1,000 random values. Here's the new example of new benchmark. Instead of calculating one value, we go over elements in the data array and calculate the result for each element. And here are the results. So you can see that the implementation using count leading zeros clearly is faster than our implementation using De Bruijn sequences. But we have to ask, or we can pat ourselves on the back and say, let's go have a lunch, and we can be done. Or otherwise, we can ask ourselves the question, what exactly did we measure there? So here is what Clang generates for our implementation using count leading zeros. It uses BSR instruction, which is byte scan reverse. it scans bit scan reverse. It scans bits from most significant digit to most significant bit to least significant bit, and returns, I think it returns the index of the bit that it found. And here's the MSVC implementation. It checks if our hardware has capability of LZ count, leading zero count instructions. And if it does, it uses it, and otherwise it uses fallback to BSR. So actually what we measured wasn't that. We measured optimized some version of optimized procedure in which the check that is reading from memory is moved outside of the loop. This is somewhat expensive load operation. So the optimizer compiler moved that out of the loop, and we don't measure it actually. And otherwise, we have everything else inside the loop. So for that reason, I'm personally not satisfied with the result, because we did not actually measure what the compiler generated. We measured something else. We measured some kind of optimized procedure instead of the initial, instead of some procedure that we can expect from plainly compiling our code into. So what can we do? We can make all our function non-line, like using these instructions, using these macros. Here, how can we do it? And here are the results. So now everything is non-line, nothing is in line. The optimization is somewhat impeded. We can see that for dummy test and my log2, which uses the Bruijn sequences, we get somewhat consistent results. But for the implementation that uses count leading zeros, we get very slow result for MSVC, which results from an inability of the compiler and optimizers to get rid of that expensive memory load. We have to load from memory every time, every call, and this makes this implementation somewhat slower than it can be. And curiously, the Clang version with BSR has relatively the same performance as our implementation using the Bruijn sequences. And well, this is some variant of result that we get that is, in my opinion, a little bit more honest or more fair, I'd say. So there is one more nuance in Clang implementation in machine code, in x86 machine code. We have BSR instruction, which is undefined, or which behavior is undefined for zero input. So we have to have a check and branch. And theoretically, if we have half of our inputs zeros, we should get a penalty, performance penalty, because our branch cannot be predicted correctly in all cases, but I could not reliably measure that. So I don't provide results about that. So maybe a solution here. And in my opinion, you should know your hardware. The instruction lead zero count, LZ count is available since Intel Haswell and AMD K10, which is more than 10 years ago. That hardware appeared more than 10 years ago. You can use compiler flags, appropriate compiler flags, for example, Arch AVX2 for MSVC, to target Haswell and excavate CPUs. You can use MIBM for GCC. You can use march Haswell or march AMD FM10 or some other capable CPU type for Clang. And in that case, all the compilers and all the compilers, MSVC and Clang and GCC all generate implementation using LZ count, leading zero count. And so here the Clang with appropriate flags. And in this case, we get truly fastest available, in my opinion, performance. By chance, we have the same results for Clang and MSVC for both for my log2 and log2 count leading zeros. And here, of course, hardware instruction count leading zeros leaves no chance, no opportunity for our handcrafted bespoke implementation using the Bruijn sequences. So probably conclusion should be know your hardware. I don't know. And of course, there is a discussion similar to what I presented to you at the Microsoft Standard Library GitHub repository about should we use check for availability of LZ count or should we not use. I advise you to check it out if you are interested. So instead of conclusion, I can just state that math is hard, coding is hard, performance is hard, measuring performance is especially hard. And I hope you can have time to scan this QR code if you want to get links to references. And thank you, I'm done.